This is Unit 2A, which is talking about exponentials. I'm just going to turn my brightness down. And these are your learning targets. So again, look at your unit overview. Make sure that you know what your learning targets are. And as you're studying, go through and actually check these off. So can you use laws of exponents, including negative and zero? Can you graph them? Can you describe key features? Can you identify scenarios, right? All these different things. These are really important as we get more and more into this unit. So use these to study and check them off as you go. And if there's something you're not sure about, go in your unit packet back to that one and try questions on that topic. But we're going to kind of go through step by step in here. So I'm going to start with learning target 1, which is using laws of exponents. There are 3 laws of exponents you need to know. And if you're in my class, I've made you dance these about 100 times. So the first one we need to know is that when we are multiplying like bases, we are adding the exponents. So multiplying like bases, add exponents. When you divide like bases, you subtract the exponents. So divide, subtract. And when you raise a power to another power, you multiply your exponents. So even if you're doing those dances during the test, as long as you know them, that's what really matters. So I'm going to go through and do 2 examples. One's a little easier, one's a little harder. They both have things that people tend to get tripped up on. So let's start with this first one. So I have 5 over 20, x cubed and x squared, and y to the 9th over y to the negative 2nd. Notice I'm kind of narrowing in on those common bases. So x and x, common bases. Y and y, common bases. These 2 numbers, however, are not common bases. And so what I want you guys to distinguish between is numbers that are just regular old numbers versus common bases with exponents we can operate on. I see a lot of people who will look at these and go, oh, well, you're dividing, so you should subtract those. You are subtracting exponents when you have a common base. Those are not exponents. So for those, I'm just going to divide that. So I'm just going to reduce this. And instead of 5 over 20, that would reduce to be 1 over 4. So just reducing, dividing the top and bottom by 5. Now I'm going to look at the x's because those are common bases. When I divide my bases, I can subtract my exponents. And that answer always goes up in your numerator. So this would be x to the 1st. And then the y's, I've got y to the 9th over y to the negative 2nd. 9 minus negative 2 is y to the 11th. And I can simplify that down a little bit. I don't need the 1. I don't need the to the 1st for the x. So this would be my simplified down answer. Again, if they're just numbers, operate with them as you normally would. If you have exponents, then think about those laws. Okay, next one is this. So I've got a lot going on here. I've got power to a power. I've got division. I've got multiplication. I've got it all. So I'm going to operate sort of on each one separately, and then I'll combine them in my last step. So looking at this first one, I'm just looking at this here. I'm going to start with that. So 24 and 3, those are just numbers. They're just coefficients. So I'm just going to divide those. So that would be 8. X to the 5th and x to the negative 2nd, I'm going to subtract those exponents. That's x to the 7th. Y to the 4th, y to the 1st. Remember, if there's not a 1 there, throw it there. It will help you. This will be y to the 3rd. So that is what that first expression comes down to be. The next one, I'm raising all of this to the 2nd power. So what I always tell my students to do is throw 1s on there. So you know that that's 3 to the 1st, x to the 1st, y to the 1st, etc. And you also don't get them confused for being like stuck together when they're not. So I do that first. Then I'm going to raise everything to that power. And when I do a power to a power, I multiply. So this is 2 to the 2nd, x to the 2nd, y to the 4th, over 3 to the 2nd, x to the 2nd, y to the 2nd. So I just multiplied each of those powers. Now I'm going to go from there. So 2 squared is 4. Hannah, I just saw your question, so I'll answer it in 1 second. X squared, y to the 4th, over 9, x squared, y squared. So again, I'm just simplifying down a little bit. And I can simplify that a little bit more too. So this would be 4 over 9. I can't reduce that. And then x squared over x squared, that would be x to the 0, which is just 1. And y to the 4th, y squared would be y to the 2nd. So this is what that second one boils down to be. So now here's what I have. I have 8x to the 7th, y to the 3rd, times 4 over 9, y to the 2nd. So multiplying those together, the x's, well, you only have one, so that's x to the 7th. The y's, I'm multiplying my bases, so I add the exponents, so that's y to the 5th. And then these two I'm just going to multiply, because they're not exponents, I'm not going to add them. That just says 8 times 4 over 9. So just multiply them. So that would give me 32 over 9, x to the 7th, y to the 5th. And you could write that as 32, x to the 7th, y to the 5th over 9 also. Those are equally correct, those answers. So Hannah said, in the first example, I kept it in a fraction. Why are we doing it all together now? So on the first example, I did keep it all in a fraction. And I did that because when I reduced the 5 over 20 here, it didn't divide to be an even number. 5 over 20 is 1 over 4. So I kept it as a fraction here because of that. On the other one, when I actually did that, this 24 over 3 could actually reduce down to be 8, right? That actually divides. So I could leave it as 8 over 1 and keep that all as over 1. That would work. But if they divide to be an even number, I don't need to be, or not an even number, but an integer, then I don't need to keep it as a fraction necessarily. You can, but you don't have to. Okay, if you have more questions with those, we can definitely come back to them. So feel free to send more questions. I'm going to start talking about exponential graphs, but again, at any time, just send away. All right, exponential graphs. Remember, guys, that you have a graphing calculator. So if I'm going to be silly enough as a teacher to give you a calculator, you guys make use of it, right? Show me how good you are with it. So here's what I want you to remember with an exponential. First of all, exponentials are either growth or they are decay. And this one in particular that you see on your screen is growth. So the bigger x gets, the faster that it climbs. Notice that down here, it's going to hug its asymptote. It will get closer and closer, but it will never hit that because we can't actually get to that point. And then y equals 0 is my asymptote for this. And remember that asymptotes are lines. So I'm actually going to make this a little thicker so we can see it. An asymptote is a line down here that it approaches, but it never hits. And so my asymptote should be a line, so you should be doing the equation. A really common question I get asked is, well, what if I said that the asymptote was 0? Would that get full credit? No, because an asymptote should be a line, so you need the y equals there. So let's look at an example, and then we'll go from there. So this first one, what is the domain, range, and asymptote of these two graphs? So the good thing about exponentials is your domain is pretty much always the same, and your range is always going to be something pretty familiar. So if I look at this graph, this is 2 to the x minus 2. Let's look at where our asymptote would be first. So it looks like it's approaching that value. And if you think about this function, that minus 2 moves it down 2. So hopefully it makes sense there that my asymptote is y equals negative 2. It's just gotten moved down 2. Now, what I would then think about is, okay, what's my domain? Well, look from left to right. So if I sweep from left to right on this function, on the x-axis, I see this arrow over here, which means it keeps going. I see this arrow up here, which means it keeps going. So that domain has no beginning and no end. So my domain here is all real numbers, negative infinity to positive infinity. My range is a little trickier because now, instead of going from left to right, I'm going bottom to top. And there is definitely a bottom to this graph. There's an asymptote, right? So this doesn't ever get any lower than negative 2. Now, does it hit negative 2? Well, we said it gets closer and closer to the asymptote but doesn't touch. So negative 2 would be the lowest it goes with a parentheses because it doesn't hit it. and then it can go up to infinity because it grows forever. So there's my domain, my range, and my asymptote. All right, we're going to do another one of those. Let's look at this one. So this is 2 to the x plus 3. And I like to think about what transformation did happen in there. It's an inside change. So it's going to be horizontal. So that moved to the right 3. So let's start with our asymptote. If I look at this, this looks like it's approaching 0, but it never actually hits it. So my asymptote is y equals 0. And that tells you a lot about your range. So we're going to come back to that with the range. Domain, again, no smallest, no biggest. So it's all real numbers. And then the range, so go bottom to top. From the bottom up, the smallest it ever gets is 0, but it doesn't hit 0. And it can go up to infinity. So definitely be aware that you'll probably get something like this and need to identify domain, range, asymptote. All right, last thing with this, let's talk about the transformations that happen to these graphs. And that's something we need to be really careful of because think about inside, outside, horizontal, vertical, right? So let's look at this first one. Take a second and just think about that. What transformation do you think happened to this parent function? So my parent function here is y equals 2 to the x. And nothing happened to that, like directly to 2 to the x, like right next to it. There's no multiplying, or adding inside. So this is definitely an outside change. This minus 2 is outside the parent function. So that's going to be a vertical change. This will be a translation down 2. Sutton asked, how do we figure out whether it's growth or decay without putting it in your calculator? We will come back to that in our next section. So that is on the agenda next, okay? The next one, y equals 2 to the x plus 3. So this is definitely an inside change. It's inside my parent function. That means it's horizontal. It's addition, so that means it's a translation. And remember, horizontal changes always go the opposite of the way you think they should go. So plus 3 means this will go to the left 3. For C, 4 to the x. So my parent function is 2 to the x. So this is really 2 times 2 to the x. This one's very tricky. Definitely above a normal typical level question. So I'm thinking about that as 2 times 2. Now, what that means is it was an inside change. So it was a vertical. Multiplying by 2 makes me think it should double. So it's actually going to get half as big. So a vertical compression by a scale factor of 1 over 2. So instead of getting twice as wide, it's going to get half as wide. Very, very tricky one. All right, and then the last one, this one's big mama. It's got all sorts of stuff going on. So I'm just going to go left to right. This 3 on the outside, that is an outside change. So it's vertical. It's multiplying, so it's a stretch. Callie, I see your question. We'll come back to it in a second. So it's multiplying, so it's a stretch. So this is a vertical stretch or vertical dilation by a scale factor of 3. So this is getting 3 times taller. Now I'm going to go to the next part, the x minus 1 in there. That's an inside change. So this is a translation to the right 1, because it's minus, it goes the opposite way. And then this is an outside change, so it's directly what we think it should be, and so that will go up 1. Now, I'm going to go back for a second to look between A and C, because Callie asked about these. She said, why is C a dilation but A isn't? And it all has to do with the parent function. So this is an awesome question. So look at this parent function. Parent function is y equals 2 to the x. So that's your original function. So here, this is my original function. The only thing that happened to it was the minus 2. In this one, my parent function is the 2 to the x. And so something happened in there to make it 4. So that's why that one's a dilation, but the other one isn't. Your parent function already has the 2 in it. So I didn't multiply in that very first one. Okay, we're going to go on to some word problems, but again, send stuff my way. This is what Sutton was asking about before, which is telling whether things are growth or decay. So I'm going to give you 3 different things, and I want to know, are these growth, are they decay, what's the initial, etc. So let's look at this first one. So I've got 1200, 1 plus 0.03 to the t. This I can already tell is growth, because look at the base of my t. This is 1 plus 0.03, which means the 100% that we started with plus more percent. So this is growth because that base there is greater than 1. So 1.03 is greater than 1. The initial value, remember that's always this. So 1200, this started at 1200. The growth factor, now factor and rate are different, right? The growth factor is this number. That's what you're multiplying by every time. So the growth factor here is 1.03, meaning you have the whole amount you started with plus an additional percent. And then the rate would be that 1.03 equals 1 plus your rate. So rate is 0.03, or convert that to a percent, 3%. All right, let's look at the next one. So 5575 times 0.065 or 0.65 to the t. Looking at this, my base there is less than 1. So I can already tell you that this is decay. My base is less than 1. Initial value, 5575. Now, again, factor versus rate. Your growth factor is just your base there. So your growth factor is 0.65. Now, what is the rate? So if this is decay, remember that decay is 1 minus r, and this is 0.65. So now I'm just going to solve for r. So that would give me r is 0.35 or 35%. So again, just think, is it growth or decay? And then set up that either 1 plus r or 1 minus r. The other way you can think about this is saying that there's 65% left. How much did you lose to get to 65%? You would have had to lose 35%. So 100 minus 65. Okay, last one. Is this growth or decay? So looking at this, I see that E looks like my base, but really that's not my base because this is not just x to the first. So I'm going to do a little playing around with my powers here. So I'm going to remember that really this is the same as e to the negative 0.24 to the x, because power to a power you can multiply. And that is really negative exponent 1 over e to the 0.24 to the x. Now, think about what that means. That means your number there is going to be less than 1. Right? That's less than 1. So this here is going to be decay. Now, you could just put it in your calculator and look at it, but that's the other way you can do it. I would urge you to always check on your calculator. Even if you want to do it algebraically, that's awesome, but check on your calculator. Initial value here is 1231. The rate of growth or decay, remember in PERT, which is what this is, it's just PE to the RT. So R is just that value up there. So R for me here is 0.24 or 24%. So because I'm using a different formula, we don't have that growth factor to contend with here. Okay, next one. And this one we're not going to spend a lot of time on. I mostly want to point out the wording. So at least in my class, we did one of these as a warm-up yesterday or the day before that said, which of these is equivalent? And when we're looking for equivalents, we're looking for them to match up, right? So what we did in class was we graphed it, and then we graphed all the answer choices, and we saw which one matched. That's what I would do for this too, but this word's really important here, which is not equivalent. So do not just do this and go, oh, that's equivalent, and call it a day, because we're looking for the one that's not equivalent. Now, you could also do this algebraically. You could look at your original and think about, well, how could I transform this? So one way would be by just distributing that out. So 2.5 minus 2.5 times 2.7. So number 1 is definitely equivalent, right? And then you could keep going from there. So like when I look at this one, that's 2 times negative 0.5, power to a power. That would be negative 0.10. So that is also equivalent. So you can keep doing it that way, right? So that's what I would urge you to do. On this one, this is to a positive exponent. So when you move it up to the top, it would be negative, so then it would match. And so it has to be 4, but the reason is because here you're multiplying your bases, so you wind up adding your exponents. So this would actually be 2.7 to the negative 2 plus 0.5x, which is different. So that's the one that's not. But again, you can graph them and just look. Okay, so let's get into some of the places where I see us having the most problems. And it's just these word problems. And the biggest struggle I saw you guys have in class was that you didn't have these formulas memorized yet. You must memorize these. This is non-negotiable. If you don't have these memorized, your chances of passing this test decrease exponentially. We know what that means now, okay? So it goes way down. So here's what you need to know. There are 3, technically. We talked about this one, A equals, or P equals, whatever you want to say. I'm just going to use Y. A times 1 plus R to the T. That's the one you learned in Algebra 1. But that is just this formula if you plug in 1 for N, which is the number of times per year. So I don't care if you don't memorize that formula. You can only memorize these 2 if you want, but you must know them. So this one is the compound interest formula. And you use this one when you know the number of times per year. So semi-annually, biannually, right? Quarterly, monthly, daily, whatever. That's when you would use this one. This one, PERT, is when it's continuously growing or decaying. Got to see that word continuous or constantly. And this one, we don't know how many times a year. Okay, so those would be the 2 I would look for. Now, if it says annually or once a year, you're going to go with that one. But that is just this if I did P 1 plus R over 1 to the 1 times T. So it's the same formula. So let's do a couple of these. And I have my handy dandy TI-83 that I nail polished all over when I was in high school. So that's what we're going to use for this. So James invested $1,500, boom, I'm already thinking initial, for 20 years time at this interest rate. How much will be in the account after this amount of time? What I'm going to do here is I'm just going to set these up. I'm not going to go through a lot of detail plugging them in because I have faith that we can do that. So this first one, annually, that is 1 time per year. So N would equal 1. So for this, I would say, okay, well, this formula is going to be 1,500, 1 plus, because it's growth, R, which is 0.0625, to the T. And that's 1,500, 1 plus 0.0625 to the 20th. So annually, once a year. All right, I'm going to do the next one. So monthly, so the number of times per year is 12. So I should have for a formula 1,500, 1 plus R. Now N isn't just 1 here, so we need to put N in, to the N times T. So this would be my formula, just basic formula. Now plugging in, it would be 1,500, 1 plus 0.0625 over 12 to the 12 times 20. All right, next one, semi-annually. Think about your semi-annual sales, twice a year, right? So y equals 1,500, 1 plus 0.0625 over 2 to the 2t. So doing this out with your actual number of years would be 2 times 20. Very repetitive once you know the formula, right? Daily, so n we're talking here is 365. So this is going to be the same thing here. Same formula, right? But I'm going to replace n with 365. All right, 2 more. Same thing here. I'm going to copy this. Same formula. And now I'm going to say, okay, quarterly, that's n times per year, 4. So that is 4 and 4. Same formula, just changing n. Now, compounded continuously. This should be dead giveaway, screaming, bells, whistles that you hear, you know. When you see this, you should be using PERT. So this would be y equals 1,500 e to the 0.0625t, which would be 1,500 e to the 0.0625 times 20. When you actually calculate that, please make sure you're using e above the division sign, that little lowercase e. Not any of the other e's you see on there. That's the only one that you want to be using. Now, I had somebody just ask, how do I know which formula to use when? So one last time. This one right here. That one is once a year, annual growth. That's it. So if it's compounding just once a year, growing or decaying, it's that. This one is when it's some other number of times. So if it's quarterly, annually, semi-annually, monthly, daily, any amount other than once a year or continuously. Now, you could also use this for once a year, and you would be just plugging in 1 for n, because n would be 1 time per year. And when you do that, think about it. P, 1 plus r over 1 is just r, and 1 times t is t. So that first one is not a different formula. It's the same one. And then this last one you would only use if we are talking about continuous growth that is happening constantly. On your study guide, there's good practice on when to use which. Okay, so let's do some harder word problems, the ones that we've been getting stuck on in class, the ones that have been driving us a little nuts. So, Mrs. Drana invests $1,000 in an account that earns 1.5% interest compounded continuously. How long will it take to triple? So, setting this up, I know that I see continuously, so I'm going to use PERT. So, first thing I would do is just write your formula. Then, I'm going to sub in anything that I know. So, let's start with what we're trying to solve for. We're trying to find how long it will take, which means t is the variable I'm trying to find. So, I should have values for everything except t, okay? So, let's start with what we know. This is definitely my initials, so 1,000. E is a number. It's not a variable. You're never plugging in for it. E is just E. Now, R, they told me the rate, and I'm going to make that into a decimal. T is what I'm trying to solve for. And it says, how long will it take to triple? So what I want to know is, when will it be 3 times what I started with? So I'm going to set this equal to 3,000. Now, this is one where we don't know the exponent. Algebraically, you do not know how to solve this yet. You need something called a logarithm. We'll learn about those in the second half of this unit. So you cannot solve this algebraically. The only way you can do this is on your calculator. So in my calculator, I would put this into y1. I would put that into y2. And then I would do second, calc, intersect. And wherever they intersect, that will be t. And t is in years here. Now, I'm not going to sit here and do this on this because you're going to be watching me type and then me hold it up. Not worth it. But if you need help with that, you can go to YouTube and search like finding intersect on TI-84. It'll pop up. Okay, let's look at another one. So slightly different. So Tara's car is depreciating at a rate of 4% quarterly. She bought the car in 2010 and it's now worth $1,300. How much did she pay originally? So think about what's missing here. Slightly different thing, right? So I'm going to just start with what I know, which is this is quarterly. So I should be using y equals a 1 plus r over n to the nt. That's the formula I should be using. I know that I want to find how much did she pay originally. So I want a. So what I'm going to do is solve for a. Plug in for every other number. So I don't know a, so that's going to stay a. 1 plus, the rate is 4%, so 0.04. Quarterly, which means 4 times a year, to the 4 times the number of years. Now 2010, we're in 2018, so that's 8 years later. And I know that it's now worth $1,300, so I'm going to set it equal. Now, I know that you could just put this in your calculator and solve, but let's do this algebraically just so we know that we can. So I'm going to just start combining what I can. So 1,300, A, and do you notice all of that is just numbers, right? There's nothing there that's like mind-blowing. It's just numbers. So I'm going to do this first. So 0.04 over 4 is 0.01. So this is 1.01 to the 32nd. And again, notice this is just numbers, right? There's no roots. There's nothing like that. So I'm going to just evaluate that. So I'm going to come up here. So 1,300 equals, my one button doesn't want to work. 1.01 to the 32nd is a nasty number. So A times 1.374940679. And now I have A times the number, right? So I'm going to divide by that on both sides. Most annoying part is writing it. And so what I get is hold on, I typed something in wrong. Okay, my calculator is bugging out, so we're going to come back to that. Okay, good. All right. Oh, you know why it's bugging out? Because this is decay, guys. Why didn't anybody yell at me? This is decay. So this should be 1 minus, and this should be 0.9. You guys got to call me out when I make mistakes like that. I know it's late, but come on, Mrs. G. Okay, so this would be 0.9 to the 32nd, which is 0.34 3368382. Divide both sides by that. Now we'll get the right answer. So 37,860.21. So again, the reason I had to fix that, it's decay, so that should have been minus in there. That was my bad. All right, we're going to do one more of these like word problems where we're just setting it up and solving, and then we'll talk about some of that time change things. So let's look at this next one. An autographed Eli Manning Super Bowl ball is increasing in value. In 2006, the ball was worth $400, and it is now worth $900. It is growing. By what rate is it growing to the nearest 0.1%? So now what I'm trying to find is R, right? So think about this. Again, this is increasing per year, so this is annual. So a times 1 plus r to the t, and it's plus because it's growth. So let's see what we know. We're trying to solve for the rate. So that's the variable I want to find. So initially it was worth 400. 1 plus r, I don't know r. T, well, how long has it been? So 2006 to now is 12 years. And it is now worth $900. So now I need to solve this for r. So before I do any sort of like rooting, anything like that, I'm going to get that root alone, the power alone. So I'm going to divide both sides by 400. And that's going to give me 1.75, I believe. No, 2.25. Close. This is what happens when you try to do math at 8:45 at night. And that gives me 1 plus r to the 12th. So now I want to keep going. I have this to the 12th. I'm going to undo that by taking a 12th root. Boom. Remember, in your calculator, just hit math and then 5. So I'm going to do the 12th root of 2.25, which is 1.069913194. And that equals 1 plus r, because on the right side, those just cancel out. Now solving for r, I'm just going to subtract 1. So r is 0.069913194. It wants this as a percent, so I do need to convert it. Move your decimal over twice. So 6.9913194. And to the nearest tenth, that is 7%. So you should be able to solve for a time, an initial value, or a rate. Any of those could be fair game. All right, send more questions if you have them. And I'm going to talk about this thing. So determining a growth rate, most of the time what I see with you guys is you're just not sure whether it should be like to the 1/10th or to the 10th, to the 1/12th or to the 12th, things like that. So here's my rule of thumb. Let's say that I have 1.03 to the x. And I want to convert that. Maybe this is yearly. And I want to convert that to be daily, right? So there's two options. And these are what's going on in your head. Year to day is 365. So either I'm going to be doing 1.03 to the 365 times years, right? Or I'm going to be doing 1.03 to the 1 over 365 years. And here's what I would encourage you to do. Think about this logically. If I do this, 1.03 to the 365, I get 48482.72453. Now think about it. Does it make sense? If it's growing 3% per year, could it be growing by that much every month or every day? It's way too much, right? So the other option was the 1 over 365. So if I actually do this, 1.03 to the 1 over 365, then I get 1.000080986. Well, think about this. If it's growing 3% in a year, does it make sense that it would be growing by about that percent per day? Yeah, the amount it grows should be smaller in a day than it is in a year. So that's the easiest way to think about this, is think through your options, right? Same thing. Let's say I'm talking about going from weekly to yearly, right? So I've got 1.9 to the x, and I want to go to yearly. So maybe this is weeks. There are 52 weeks in a year. So I could either be doing like 1.9 to the 52y or 1.9 to the 1 over 52y, right? Those are my options. So think about it. What makes more sense? If it's growing by this much per week, and I want to know how much it grows in a year, it should grow more than that, right? So if I raise this to the 1 over 52, it's going to be smaller. But if I raise it to the 52, it's going to be bigger. And so that's how I'm selecting like which one makes more sense. Think to yourself, what makes more sense? Should this be getting bigger or should it be getting smaller? Okay, so let's look at a problem. And again, these are all kind of the same. If you need more practice, look at that Math Bits worksheet we worked on, or ask me for more practice and I'll send it to you. So a student studying public policy created a model where the population decreased by 25% over a decade. So what I'm talking about here is 0.1 minus 0.25 to the decade. So this is my formula, right? That 0.75 is 1 minus 0.25. So she wants to know what it would be after Y years. So again, think through this. You have two options. Either you're doing 0.75 to the 10y, or you're doing 0.75 to the 1/10 y. Now, if it decreased by that much per year, or per decade, it should decrease by less than that per year. So that's why I know it has to be this one, because that's the one that's going to make it less. And also because a year is 1/10 of a decade. So I'm choosing the 1/10 one. So now what I can do is I can say this. The 714 doesn't change. So it would be 0.75 to the 1/10 t. And I'm going to do 0.75 to the 1/10, which is 0.971641657 to the t, or sorry, to the y, which is answer choice 3. Now, let's say that they asked you for the percent that it was decaying in a year. This is your factor, right? So to find the percent it was decaying, it's decay, so it's 1 minus r, and I would set that equal to this. Solve for r, so that would give me 0.028358342. Rate of decay would be about 3% per year, 2.8-ish% per year. 25% over a decade. Those are hard. Those are tricky. So if you need more help, come see me, go see your teacher, send me questions. But I totally agree that those are tricky. And I think you guys are honestly doing awesome on them. All right, last thing, which is the very last thing we did, which was solving for a variable when you have exponential equations. So if you already have a common base, then the idea is if the bases match, the exponents should match. So if I have 5 to the x plus 1 equals 5 to the 10, then x plus 1 needs to equal 10, because your bases are the same. So x plus 1 needs to equal 10, x needs to equal 9. And you can always check yourself, plug it back in, make sure you got it. Same thing for this one. I've got 12 to the 2x minus 5 is 12 to the 3x minus 2. So since the bases match, I need my exponents to match. And then I'm just going to solve. So 2x minus 5 is 3x minus 6. Add 6 to this side, that gives me 1. Subtract 2x, that gives me x. So x equals 1. And again, plug it back in and check it, by all means. The harder case is this one, and we're going to do 3, and then we're out. I'll just take more questions. So these bases don't match. So what we need to do is a little bit of magic to get them to match. So what I need to think of is, what are these both powers of? 3 and 9 are both powers of 3. So this I'm just going to leave as 3 to the y plus 1. But 9, instead of 9, I'm going to replace that with 3 to the second. So again, this side stays the same. This side, you're doing a power to a power, so you multiply. Make sure that you distribute that out. And so I get y plus 1 equals 2y minus 2. And then solve from there. So this would give me y equals 3. All right, 2 more. Next one. I need to ask myself, what are these both powers of? 27, 9 are not integer powers of each other. There might be some cool fractions we can work with, but again, like you're only going to get that by guess and check at this point, so don't sweat that. But they are both powers of 3. So instead of 9, I'm going to write 3 squared. And instead of 27, I'm going to write 3 cubed. So this becomes 3 to the 6x plus 2 equals 3 to the 3x plus 6. Once your bases match, then your exponents need to be equal. So I get 3x equals 4 and x equals 4 over 3. A fraction does not mean you're wrong. It just means it's a fraction. So do not worry if you get a fraction. It is okay. All right, last problem, and then I'll just hang around for questions, is this one. 5 to the 3x minus 1 equals 1 over 125. What are they both powers of? Well, a good guess is, I see that 25 in there, 125. Maybe they're both 5. So I'm going to leave this alone. And 5 to what power would be 125? Well, 5 times 5 is 25. Times 5 is 125. So that's 3. What kind of exponent makes it flip over? Must be a negative exponent. So now my bases match. So now I could say 3x minus 1 equals negative 3. 3x equals negative 2. So x equals negative 2 thirds. All right, guys, that is all I have planned. That is a big overview of everything you might see on the test. If you have questions, I'm going to hang out for about 4 or 5 minutes, see if there's anything else you guys want to ask. But otherwise, thank you for watching. We had a ton of people on tonight, which is great. And if you're watching it on the replay, that's awesome too. And I will see you guys soon.